Hey guys, it's been a while, and I'm just here to say that we are still alive and kicking, and we just needed a month off on the one hand to prepare some content for the Houdini 17 launch, which went really great, also thanks to you guys and your amazing feedback, and on the other hand, we are preparing some new courses for this Patreon here, which admittedly takes a bit more time than we anticipated. And one of those courses is going to deal with DOPs, with grains, and also with vellum. And while I'd love to release the course, there are still some bits and pieces I have to complete beforehand. So what I want to give you today is kind of a preview. So I'm taking one of those tutorials that I prepared for the course and just releasing it here. Not necessarily the order that we intended with this course. However, just to give you an idea of what kind of topics we're dealing with. And also, the tutorial we're releasing today is a production problem. So it's a problem I had to solve for a recent project. And I think those kinds of problems are really helpful to you and to the whole community. So thanks for staying with us. Thanks for supporting us, and let's get started.
So, as I mentioned, this is a production setup which was built for a shot I was working on with the super talented Vincent Schwenk and Vitali Grossman. Cheers to you guys, and check out their portfolios, I'll link to them. What we want to do here is control a cloth that is simulated by vellum and control its constraints and change these constraints while it's simulating. So, let's start out by creating a grid, which will serve as our cloth, scale it to 2 by 2, and increase its row and column count to 100. Let's disable the grid here, and after that, attach a vellum cloth. Just leave those settings as they are currently. And what I want to do first now is I want to pin this edge here. So I need a group containing only the points of this grid that form the edge. So before we go into the vellum cloth, let's drop down a group, wire this in, uncheck the base group, select points, call the group edge, and select include by edges, and down here check unshared edges. So when I highlight this, I can see I've got my edges selected here. In order to pin those edges, let's drop down another vellum constraint here. By hitting Shift Enter, it'll automatically attach it, so I don't have to rewire these 3 inputs here. And I want to set my constraint type to pin to target. Pin type should be permanent for now, and I'd like to highlight this and then select group type points and select the edge group here. Let's just check by attaching a vellum solver, highlighting it, dialing down the constraint iterations a bit. It's a really simple sim, and hitting play. So yeah, that's our standard cloth behavior, not very exciting, but it does what it should. So what we could do for now to increase the likeliness of some creases here, some folds appearing in the vellum cloth constraint, let's increase the rest length scale to say 1.3 and resimulate that. Okay, so that's working as expected too. So we want to pin some of those points here while they are simulating. So let's first select those points that we want to pin. And in my case, I will use a font to drive that. And let's highlight this font here, attach a transform, and rotate that by -90 degrees so it sits in the same plane as my cloth. And what I want to put in here is an expression, so backticks. I would like to round my current frame count, which I divide by, let's say, 25. So this, backticks, yeah, like that. So what we have now when we hit play is a number that increases every 25 frames. Let's maybe scale up the font size. And as I only care for the outline of the font and not those additional polylines that are generated by holding those faces here, let's uncheck hold faces, which for now will result in this weirdly looking poly shape. However, what we're going to do is we're going to drop down a poly wire down here, which will wire up, highlight this, and we now only take the outline that's been created into account. So dial back the wire radius a tiny bit and increase the division to say 8. Also, I want to uncheck prevent joint buckling. So I'm going to use that to select my constraints, which I want to pin. So to create those, I will add another vellum constraint in here after the pin that pinned all the edges and the vellum solver. I'll create another pin constraint. Don't want to change anything to the grouping here. And I want to set the pin type to soft. So this pin in essence is like a rubber band or a spring that's pulling those constraints towards their position. And also I want to enable an output group for the stretch parameter here. And let's call that pin stretch. So when I highlight my vellum solver now, and let's reset this to frame 1, we see our plane behaves as if it was just not simulating, just really stiff. That is because this pin constraint here has a high stiffness and pulls those points to their original position. So once we lower this stiffness here to, in our case, say 0 and hit play again, we can see now those pin constraints don't have any effect at all. And this property, the stiffness, is what we're going to animate and what we're going to use to drive the constraints. So what I'll do is I will drop down a group again, and in this group node, I'll wire in the constraints coming out of my pin here. And I want to use this polywire here, increase its radius a bit to 0.03, so we select all those points, and let's select those constraint points here, call them fix, uncheck base group, and check keep in bounding regions, and we want to keep them by bounding object here. Let's highlight this one, and we can see through the erroneous display here, that's working. I'm selecting those points here. However, for my constraints, as they are primitives and all their attributes are on primitives, we have to promote this group from points to primitives. I want to promote the group fixed. Highlight this, and we can see now we've got those primitives selected here. Let's just hit play to see if that works with the animation. Yes, that is working fine. Okay, that's all we need to do to those constraints here. So basically what we're doing is we're just selecting them. And then let's dive into the Vellum solver. And when diving into the Vellum solver sub, we end up a few subnets deep into the actual solver. So this is inside a subnet of a hidden DOPnet that actually forms the Vellum subsolver. And what you can do in here is drive forces. And not only drive forces, but also drive geometry in general. And also drive constraint geometry. And the way I want to do that today is by using a geowrangle and a bit of vex code. So the geowrangle takes in any geometry or accesses any geometry within a DOP network and modifies it, just as your normal attribute wrangle would in SOPs. However, we have to take care of some things first. In this case, under data bindings, I'd like to not bind the geometry, but the constraint geometry. So I will work on those constraints here. And then I want to update them using those groups coming into my second slot. So input 2 should be the second context geometry. And that is referencing anything that's coming in through this slot in the Vellum solver here. So let's dive back in. And we want to run this over primitives, as the constraints are primitives. So now what we want to check is in which group is our constraint primitives. And to do that, let's go up one level. I'll have to access a given prim number. However, those prim numbers are not stable, so they change a bit when being imported into the Vellum solver here. So what we have to do first is drop down another primitive wrangle. And before we do all the grouping fun here, let's just create an ID attribute that is equal to the primitive number. So now when we highlight this, we can see we have an ID here that is exactly the same as the primitive number. And we can use this ID attribute to access the correct primitive in our Vellum solver, in our geowrangle. So let's dive back in. So what we want to do here is, for each constraint while we're simulating, we'd like to check if it's in that fixed group, and also if it's a constraint that belongs to the pin stretch constraint. So we got to check if our primitive is within two groups. So let's check if our primitive is in the prim group, coming in through our second slot, the one with the ID 1. Call it pin stretch. And instead of the prim number, let's use the ID attribute. So if it's within that group, and if it's also within the group fix, that's the one we selected with the font sub, then we want to set its stiffness value to something really high, so it'll get pinned to the original position. Let's set it to 1 billion. And else, if the constraint is only in the pin stretch group here, so we're only dealing with those constraints that drive this second pin stretch. If it's only in that group and not in the fixed group, then let's set our stiffness to 0, so it can move freely. Spelling error here, that's looking better. Let's head up one level, highlight the Vellum solver, and keep our fingers crossed. And we can see that is running. Okay, let's go over the setup one more time really quick. We're creating a grid, grouping those edges, then configuring a standard cloth for the whole grid, then pinning only the edge points here with a permanent pin, so they will always remain there. And then for every point we create a soft constraint that can be used to constrain the point's position to its original position. And by default, we set its stretch stiffness to 0, so the points basically can move around freely. After that, we select the stream with our constraints and create an ID attribute on every primitive in our constraint network. just to be able to correctly address this or to correctly access this constraint within the Vellum solver. Also, using our font node with a bit of old school HScript expression in here, we build an animated font, transform it so it lies in the plane, build geometry out of its outline using the polywire, and use that to build a point group within our constraint network, which will then convert into a primitive group here. And with that primitive group selected, inside of our Vellum solver, all we do is we make sure we are only working on constraints that are within the pin stretch group. That's the group containing all those soft constraints, and specifically all those soft stretch constraints. And if a given primitive is in that group, we either set its stiffness value to 0, or if it's also in the fixed group, that's the one we selected with the font, we set its stiffness to 1 billion. So it's really strong and wants to be pulled back to its original position. And that is all we're doing here. Keep in mind that when you want to work on the constraint geometry, in the GeoWrangle set the data binding to constraint geometry like this, capital C, capital G. And also, if you want to access data coming in through one of those Vellum slots, you need to set up those bindings here in the Inputs tab. So that is one way of doing constraint animation in Vellum while it's simulating.